In this video, we're going to be looking at some of the nuances of double displacement reactions. As we know, the general formula of a double displacement reaction is two ionic compounds in which either the anions or the cations switch places with each other and give us two different ionic compounds. Now, the way that we normally do double displacement reactions is we take one or both of the ionic compounds, pour them into water, and watch them dissolve such that we have solutions of our ionic solids rather than actual solid compounds. And then when these solutions are mixed together, it's possible that when the two solutions are mixed together, one or possibly both of the ionic compounds that we make does not actually dissolve completely, as we can see from this reaction here, where we mix a solution of silver nitrate into a solution of sodium chloride, and because silver chloride is a compound that does not dissolve completely, we see it appear as a cloudy layer that forms within this solution, showing that these silver chloride particles do not dissolve completely. This phenomenon is what we call precipitation, as in the same term that is used to describe water falling from the sky, and the name of this solid that we form is what we call a precipitate. Now, precipitate formation is actually rather predictable with the aid of something that looks like this, which is what we call a solubility table. The way that we use a solubility table is we first look at the anion of the compound. So if we consider the precipitate we made in the example reaction above, AgCl, Cl- is the anion in this. So if we go and find chloride, which is the name of Cl-, we can see how chloride compounds can be soluble or insoluble. You will notice that instead of insoluble, which means not soluble, insoluble compounds are referred to having low solubility. The reason for this is that no compound is completely insoluble. Silver chloride will dissolve with very, very, very small amounts when put into water, but generally water is not able to separate the silver and chloride ions from each other for most of the silver chloride that is poured in here. So because most compounds have at least partial solubility, low solubility simply means that most of it will not dissolve. Now, if we look here, we see from this solubility table, determined experimentally, that several ions, several metal ions, cations, when paired with chlorine, produce precipitates that don't dissolve completely in water, and chief among those is silver. So we can use this table to show that when chloride is paired with silver, it produces a compound with poor solubility. However, all others apart from these 5 metal ions here, when paired with chlorine, produce compounds that are fully soluble in water. To demonstrate how we use this solubility table, it's always best to try an example. So if we consider the following double displacement reactions here, we can use our general formula AB plus CD goes to AD plus CB in order to come up with the hypothetical products for both reactions. So if we were to switch the cations, sodium and potassium, in the first reaction, we would end up with Na2SO4, sodium sulfate, and potassium chloride here. And a quick cursory glance will allow us to balance this so that we have 2 sodium on both sides and 2 potassium on both sides. And then it's implied that both of these would have 1 of each. Next up, we can consider what happens if we switch the hydrogen and silver ions between AgNO3 and HCl. If we do this, we would end up with AgCl, which again, we know that this is going to form a precipitate because we tested it before and because it was similar to our previous example, but let's go through the motions here. and the hydrogen switches with silver in order to produce HNO3, nitric acid. So, if we wanted to determine which compounds will form a precipitate, we can go back to our solubility table and check. Remember that it's always best to start by looking at the anion because of how the table is organized. So the compounds that we're looking for are silver chloride, nitric acid, sodium sulfate, and potassium chloride. So we have two chloride compounds here. We have silver chloride, which we know is going to form a precipitate here, and we have potassium chloride. So if we look at our anion chloride, we do not see potassium on the list of ions that produce compounds with poor solubility, which means that the potassium ion must be in here. That means that potassium chloride is going to be soluble, and we're not going to see a precipitate, which is not similar to how silver chloride is going to work. Next, if we consider our sodium sulfate, we can find where sulfate is here. We can check the ions that do not cause a soluble compound to form, and we see that sodium is not on that list. Therefore, sodium must be under the all others category, and therefore sodium sulfate is a compound that is fully soluble within water. Next, we can go up and check nitric acid. Nitrate is an easy compound to check because pretty much every nitrate or every cation that is paired with nitrate is going to be soluble. Therefore, HNO3 is also going to dissolve. So if we go back to our reactions, we can put the states of matter in where silver chloride is the only precipitate we're going to get, and every other compound is going to stay dissolved in water. Therefore, in chemical reaction number 1, there is no precipitate here that forms. Now, if you consider this, when we mix these two solutions together, both of these are solutions, and both of them are completely colorless in solution. And when we pour two colorless solutions together, there is no precipitate that forms, which means that we're not going to see anything. Now, because both of these exist dissolved, that means that in both of these compounds, the ions are going to stay separate from each other. Now, because we don't actually get a solid precipitate that forms, that means that the ions that have separated in the reactants are going to stay separated in the products, which effectively means that neither of the reactants has changed, and therefore that we are not going to see a visible reaction if we do not have a precipitate within. However, in reaction 2, that's not true because we get the silver chloride precipitate. Therefore, the ions that separated in the reactants actually do not stay separated in the products because the chlorine from HCl and the silver from AgNO3 come together in order to form a solid compound, which means that the reactants have definitely changed. Now, for this reason, reactions that form or reactions that occur without forming a precipitate, we can effectively say that they do not occur because there is no visible reaction to show that the ions have changed. And therefore, because there is no change to the reactants, we cannot observe that any reaction has taken place. In the next video to this, we will look at what happens in double displacement reactions that have subsequent reactions that occur.